Hello everyone, it's Benny, and welcome back to the Advanced Redstone Computer Series. In this video, we're going to start talking about the standard Redstone Computer Instruction Set, version 2.0, because version 1 sucked. And it's the instruction set that we will be using for our humble processor. So, if you don't care what instruction set we're using or how it works, which is probably a terrible idea if you are considering, but hey, I'm not one to judge, so it's your decision. But if you don't care, you're free to skip this video. But for those of you who do care, you all are deserved a warning, because that's totally proper care. Anyways, and that warning is, I am going to be mentioning a few topics which probably won't be covered until much, much later in the series. Because hey, the instruction set is supposed to encapsulate every function you can program into the processor. And that's also going to include some programming topics in some respects. So, just be warned ahead of time. Don't freak out and be like, oh no, what the hell is a pointer? What am I supposed to make of this? And yeah, don't worry about that. It's all going to come just in about 80 videos or so from now. Yeah, probably not that bad, but we'll see. Anyways, back on the main topic of the video, standard Redstone Computer Instruction Set version 2. Let's begin. Okay, so, standard Redstone Computer Instruction Set version 2, hereafter referred to as SRCIS because that name is just way too long. The first thing I'm going to talk about is the bit layout, which contrary to what some people believe, is not the entire instruction set. If your bit layout is your entire instruction set, and you're an exception to that rule, your instruction set, in all likelihood, sucks. So you may want to rethink a few things. That's all I'm going to say about that. So here's just the bit layout, not the entire instruction set, just the way the bits are laid out. Which bits mean what, and what certain bits will do to affect the overall instruction. So, SRCIS has a 16-bit instruction system. That's total number of bits in the entire instruction. There's 16 bits. And in these 16 bits, there's 4 sections. Each of these 4 sections is 4 bits. Nothing to get too confused over. 4 sections of 4 bits. Pretty easy. So first section, it's the function. This is probably what you're thinking of when you think of the instruction. It's the part of the instruction which actually tells the processor what to do. If I want the processor to add 2 numbers, I tell it in the function. If I want it to multiply 5,062,782 and my 0, I tell it to do here. It's all the function. This is what I'm telling the processor, hey, do this or else. That's the function. Next to the function, we have register A. Now, this comes from the fact that the vast majority of functions take more than one input. If I want to add something, I can't add just 5. I can't just add 5. That doesn't make any sense. How do you simply add 5 and nothing else? It doesn't work, right? Right. So that's why I have 2 registers. Register A and register B. Register A, that contained 3, and register B, that contained 5, and my function was addition. Then hey, it would say, okay, now I know how to add. I can do 3 plus 5, and it's all happy and magical. But where does it save that? Where does it save this elusive result of adding 3 plus 5? And that's where the register output comes into play. If I want to save it somewhere else, which a lot of times you do, is where that comes into play. I want to add 3 plus 5, I want to save it into the remote foreign corner of the register system. That's what I do here. So yeah, it's a fairly easy layout, even if it is a bit confusing at first. And just to help you understand a little bit better how it works, I've built a mock instruction panel where we're going to do some mock processing. So first up, function. What function do we want to do? It can be literally any function we want, because at this point we haven't hooked it up to anything yet. We haven't set anything. I, however, am going to do the ever so imaginative OR function. And I'm going to say that's function code 8. So if 8 is the function code for OR, putting this in means, hey, processor, I want you to OR the 2 registers I give you. So register A, what do I want register A to be? What number should I OR? I'm going to OR 2, whatever number's in register 2, but whatever number's in register 3. And I'm going to save that to register 4. Pretty straightforward. So, as you can see, I have my super hyper complex micro mock processor. I know, it's amazing. As you can see in register 2, we have 3. So if I'm going to load the 2, and it actually can perform the OR function. I just have to load both registers. So load register 2, load register 3. It's performing the OR function, and as a result of that, we get 7. So we get to write 7 into our output register, register 4. I know, this is like mind-blowingly complex processing right here. But hey, just for fun, let's do something else. Oh, what should we do? Let's subtract. Why not? So, let's take function 1, which, let's say that's subtraction. And I'm going to subtract, let's use what we just got. Let's subtract 4. Why not? We can subtract from register 3. We can save it back to register 4. Why not? So 4 minus whatever's in register 3. So register 4, that's 7. Going to do 7 minus whatever's in register 3. That's 5. And the end result of all that happens to be 2. So 3 minus 5 is 2. And I'm going to save that back to register 4. And there you go. So hopefully that gives you an idea of the bit layout and a little bit of idea how a function is traced through the processor and the SRCIS instruction set. So yeah, that's the gist of it, and hopefully that gives you a little bit better understanding. So, if all you care about is using the instruction set, that might actually be enough to get you by. But no, we can't just stop there. We're going to go into all the technical nitty-gritty of whatever makes up this instruction set. Because, hey, we're going to actually be building this thing. This stuff is going to matter to us. So, let's go ahead. Let's do that. Alright, so this right here is the entire SRCIS 2.0 specification. I know, it's a giant wall of text, and I promise it's pretty simple. There's only 2 things in this giant wall of text. The function over here, and the registers over here. That's it. That's the giant wall of text. I promise, not that bad. So, first off, I'm going to go over the functions, because gotta start somewhere. And why not? So this is an enumeration of all 16 functions that SRCIS 2 can perform. So, let's go through them all and see what they do. Now, they're already labeled pretty conveniently. There's the name. This is the name of the function. The use, what the function actually does, at least as best you can put it in a single line. And code. What binary code do you input to use the function? And it's amazing, but it's in numerical order. So, if you want to look up a function, it's pretty easy to figure out which one it is. But anyways, let's look at all the functions. So, number 1, add. You'll never get what this function does. That's right, it takes register A, adds it to register B, and saves it to the output. Subtract, we actually demonstrated this one. Takes register A, subtracts register B, saves it to the output. Incredibly straightforward. Now shift left, what this function does is, technically it adds A and B, although really you should only use it with one of them, but hey, if you put in 2, it'll add them, so yeah. So A and B, you add them together. So, let's say I'd add A and B in 8, then I shift it to, actually I shift it to the right, I suck in left and right, so just don't even worry about it. But yeah, it shifts it to the right, and it goes over 1. Now this function I'm eventually going to replace with a barrel shifting command, but for now, it can just be shift right. But yeah, it's very soon to be obsolete. So next is the call function, which I'm going to completely ignore from this point, because it's by far the hardest function to understand in the entire instruction set. And really you have to sort of understand the entire computer to really understand it. So we're just going to pretend it doesn't exist. So call function doesn't exist. Next up is the branch if equal command. What's branching? I'll explain when I'm done with functions. But this one branches if we're equal. So I'm going to load A and B. Let's choose an input. So register A, number 4. Register B, number 3. Let's compare them. So register 4, register 3. Register 4 is 2, register 3 is 0. Guess what? They aren't the same. So, sorry, no branching for you. Maybe next time. In fact, yes, next time, because next command is branch if not equal. So what this does, takes register A, takes register B, they are not equal, it's going to branch. So be prepared for that. But yeah, you shouldn't have too much trouble with these commands. They're pretty straightforward. Branch if greater than. This is also pretty straightforward. Take register A, still 4. Take register B, still 3. 4 and 3. If register A, 4, is greater than 3, hey, guess what? 2 is better than 1. Wait, no. 2 is greater than 0. So, guess what? we're going to branch. And yeah, pretty straightforward. Branch less than, same thing, except you're branching if less than instead of branching if they're greater than. Really straightforward, should not have any trouble with this. Pretty easy. Or, we already demonstrated this one, very easy. Takes two numbers and ORs them together. I'll demonstrate it again, because why not? I'll stretch up the inputs too. So 2 and 5, the ones we weren't using. So 2 and 5. In this case, they're both 2, so nothing changes. But yeah, it's just ORing them together. Pretty easy to understand. And a little bit trickier to understand for some reason. A lot of people have issues with this. So I'll do 3 and 5, because that's actually... Actually, will I do 3 and... Wait, why is everything 2? That's boring. Let's do 3 and 5, and I'll do 1 and 2. Or 3 and 2. Yeah, so I'll do 3 and 2. Why is everything 2? That's boring. So 3 and 5. That's what's in registers 2 and 3. So what this will do, simply enough, go to each individual bit and AND them. So 1 and 1, that's 1. So there's the output. 1 and 0, that's 0. There's the output. 0 and 1, still 0. That's the output. 0 and 0, 0. There's the output. So this is the output of ANDing them together. It's the only bit they have in common. So it's the only bit that gets through. Very straightforward. And you might be wondering what some of these functions are actually useful for. Don't worry about it. That's all sort of programming stuff, and I'll get into that when we actually get into programming. But trust me, they're pretty useful, or I wouldn't have bothered putting them in here, because come on, I only have 16 functions, so yeah. Next function is NOR. Guess what this does? It takes OR and inverts it. So A or B and inverts it. Not even going to demonstrate it. Super easy. XOR. Trust me, you should probably know what an XOR gate is if you're starting the series. But yeah, it does the same thing between every single bit. Again, pretty straightforward. None of these functions are really that difficult, except the call function and some of the later functions. Next up is saving. This is where we actually access RAM. This one actually is a little bit weird. So first off, I'm going to input proper function code. So proper function code for saving is 1100. It also has the single most insightful comment anyone has ever added to my plot. So let's just stand in awe of this for a moment. And that's way too much of that, so let's just keep going. So I'm going to save. Register A, that's going to be the register that holds whatever memory address we're saving to. So I'm going to say register 2. That contains the address I want to save to. Register B, this is a register that contains what data I want to save into that RAM cell. So let's say that's contained in register 3. Register output, if I'm not mistaken, it's absolutely meaningless in this command. Could be wrong, but pretty sure it's absolutely meaningless. So yeah. So I'll do register 2 and 3. So what this will do, register 2, that's 3. So let's say this is my memory cell. Each of these dots of redstone is a memory address. I loaded 3, so it's going to go to address 3. 0, 1, 2, 3. 3. This address right here. And it's going to take whatever data is in this register, register 3. So I believe that was register B, right? Yes. So take register 3, that's, in this case that's a 5. Save it there. So 0, 1, 0, 1. Now I've written at register 3. That's a save command. And it'll do that for whatever memory address you put in. Not that hard of a function. It's a little bit tricky, but you shouldn't have too much trouble picking it up. It's not the hardest function in the world. Really, yeah, like I said, only the call function is a little bit tricky. Loading is a bit different, so be careful. This register A, again, is the memory address you're using. Yes, definitely what I meant to say. Definitely didn't take me that long to say it. That didn't happen. It's all your imagination. Register B, absolutely meaningless in this case. So don't try putting anything in register B. It's not going to happen. Well, it's going to happen. It's just going to be useless. Register output. This is where you're going to put whatever register you want to save the data from that address in. So my output register, 4, because 4s are cool. So register 2, again, is my address. So I'm going to go into memory, going to find address 3, 0, 1, 2, 3. And I found address 3. So I'm going to take this data, which is 5, gonna put it in, and that's going to be saved to register 4. So congratulations, 4. You now represent the proud clan of 5s. And yeah, don't know what that's all about. This is why I shouldn't record videos at late at night, but oh well. Const. This is the way of putting constants into the program, into the computer. This one, again, a little bit weird, so be careful. I should have put that in, but yeah. Constant function is 14, right? Right? Right, okay. So, here's the way this works. Register output, is that actually meaningful in this case? I'm trying to remember. I'm going to double check the function. Input constant, let's see, constant loads A and B is an input number. Yeah, okay, register output is important, never mind. Just double checking. Hey, I want to give you accurate information, so don't yell at me for not memorizing my instruction set. Register A. So this actually has nothing to do with register A. This has nothing to do with register B in this case. These are all part of your number. You're inputting an 8-bit number into the system. These are the 4 most significant bits. These are the 4 least significant bits. So let's say I want to put 3 into the computer. These are least significant for 3 bits, so that's 1, 2, 4, 8, 16, 32, 64, 128. That's the way this works. Now, output is wherever I want to save that to. I want to save it to register 2. Actually, I want to put 3, because I want to save 3 in register 3, because, I mean, that's just awesome, so why not? So I'm going to input a 3, and it's going to save register 3. And I've just input a constant into my super, hyper, mega, micro mock computer. And yeah, if I want to put in a really big number, let's say I want to put in 225. So that's 128, 192, 224, and 1. So this is just like reading an 8-bit number, except it goes like down like that. Not that hard. I'd save that to a register, but I don't have enough space to actually save that in this case, so that would be kind of useless. But yeah, you get the idea. Now, end. This is the hardest function in the entire computer. Guess what it does? No, just guess. Yeah, I know, it's not that hard. I'm over-dramatizing it. It ends the program. So this will just end whatever program you're running. Pretty easy. So yeah. And that's pretty much all the functions this thing does, except for the call function. But again, going over that at the end. Alright, so we've covered every single function in the entire computer, except the call function. But don't worry, I will remember that. So now let's talk about the wonderful world of registers. Much simpler, not nearly as complicated, although every single register does have its own special purpose. Sorry, that's just the way it is. So yeah, there's 16 registers in the entire system, and every single one does something a little bit different, but most of them are so close to the same that you won't even notice. So yeah. So first off, there's name, use, and code, just like before. And code, again, in increasing numerical order. So should be pretty easy to figure all this out. But yeah. First up, the 0 register. There's something really special about this register, and it's summed up pretty well right here. It's always going to be 0. So if I put in 0000 into the register system, I'm always guaranteed to get a 0. That leaves the question, what happens if I try saving to the 0 register? Well, we're going to make it so that crashes the computer. Because no, you can't save to the 0 register. It's 0. It's going to stay 0, and it's always going to be 0. It's 0. Deal with it. Next register, OR, the 1 register. Guess what this one does? It's always going to be 1. And that's, again, code 1. So, that's kind of neat. If you want a 0 for some reason in your program, put in 0. If you want 1 for some reason in your program, put in 1. Pretty easy. And yeah. And again, you try right into this, it's going to crash the computer. Because no, there's a 1. Deal with it. So next up, the program counter. This one's a little bit interesting. What this register does is the number in this register is going to always be whatever line of code you're reading. So if I'm on line 0, this register is going to hold 0. If I'm on line 100, I'm going to be reading line 100 of code. So that's the special thing about this register. It's whatever line of code I'm on. And every cycle, guess what happens? This goes up by 1. So it just keeps reading line of code sequentially. It's pretty easy, actually. And here's the neat thing. If I want to jump for some reason, if I say, you know what, screw it, I want to be on line code 200 instead of 100, all I gotta do is gotta write 200 to the program counter, and I'm automatically, I should say, on line 200. So it's a pretty neat system. And this is, whoops, sorry about the mic. This is sort of where branching starts to come in, with the next register, the jump register. This acts for the most part like any general register, but if I branch, whatever numbers in the jump register automatically save to the program counter. And you know what that means? That's right. I can save any line of code I want to the jump register. And if I branch, that automatically becomes a line of code in the program counter. So it's really nice branching system. So for example, because that's a little bit confusing. Let's say program counter, where should I build this? Doesn't matter. Let's say my program counter right now contains 2. And my jump register contains 14. Now the next command, normally I go to line 3, but let's say line 2 is special. This has branch if equal to 0 register and 0 register. No idea why you'd waste your time doing such a pointless command, but hey, you're a badass programmer, so why not? So that, of course, is going to branch because 0, amazingly enough, does end up being equal to 0. So what happened in this command is you'd overwrite the jump register with whatever is in... Wait, you overwrite the program counter for whatever's in the jump register. So all of a sudden, you're magically on line 14 next time. Because you're the programmer, you decide you want to be a badass. But hey, it's good a reason as any to branch, I suppose, so why not? And yeah, now I gotta destroy all this without destroying my plot. That's always fun. But yeah. So, and those are only the really special registers. Everything else acts mostly like a general purpose register. So, next up is call C1 for C4. These are all used in the call function. What do they do? It's a mystery. We'll talk about it in the call function. But for every single purpose, even when you're using the call function, pretty much, they're any register you'd want. They're general purpose registers, and they don't matter for nearly every single case. So they're not that hard to learn. But yeah, they pretty much act like every other piece of memory I've used in this demonstration in the video. So yeah, these, yeah, again. But they do have some purpose in the call function, which I'll talk about when I talk about the mysterious and magical call function. Which actually is pretty mysterious and pretty magical, but yeah. So next up, we have a bunch of really interestingly named registers. AX, BX, CX, DX, SI, DI, BP, SP. If you've ever programmed x86 assembly language, you already know exactly what these things do. If you've never written x86 assembly language, then as far as you're concerned, you don't care what these things do because they act like any other register in the world. I'll talk about what they do when I'm dealing with programming, but for all purposes here, doesn't matter. They act like any other general purpose register, and you don't really need to know what they are when you're building your CPU. So yeah, I'll talk about these when you're programming. But just so you know what they are, there's the accumulator, the base, the counter, data, source index, destination index. Couldn't fit an index on there. So yeah, base pointer and stack pointer. That's what they're called. That's what all the meaning behind the name is. What do they do? Again, who cares? You're designing the hardware. You don't care what the programmer does with them. And for the most part, the programmer doesn't care what they do with them either. So it really doesn't matter. Like it says here, first 8 are only truly specialized. Really, only first 4 are truly specialized. All others are just suggestions, so you can use these registers however you please. And yeah, those are the registers. Not nearly as hard to understand as the functions, but yeah. They're not that hard to keep track of, so hopefully they don't give you too much trouble. And that brings us to the moment we've all been waiting for. The dark, the mysterious, the magical, the awesome call function. I know, those are some really dramatic speech. I should be like a speechwriter or something. But anyways, the call function. Now that you understand what the whole system does, this is going to be a lot easier to understand. If you've ever written in some programming language or some scripting language before, you might know of functions, where basically you'll be writing some code, and then all of a sudden you say, you know what, screw it. I want you to exit some other code that's in some completely different location, and then keep reading the rest of my code like normal. That's basically what the call function does. So for example, if I'm on line of code 2, basically, instead of just branching like normal, I say, okay, I want you to branch off into this entire separate program. And I want you to read a whole bunch of code there. So ... These are my Redstone ellipses. I know they're super fancy. And then, after you're done executing all that code, so in other words, once you reach the end code right here, then just go back like normal. And go to line 3 and just keep reading like nothing happened. That's the call function. And, yeah. The only real difference is, it doesn't necessarily have to be code. I might say, you know what? I don't really like this instruction set. I mean, I want to do multiplication a lot. This doesn't have any multiplication instructions. So, what you'll do, build a multiplier, and access it with the call function. That's right. You can access external hardware with the call function. I want to use a GPU, you can access it with the call function. And you can still do this with memory mapping if you don't like using the call function, but hey, the call function's there just for fun. So yeah, you can use the call function to do that. What it's really, really useful for, where it's used for things that you can't really do with anything else, is things like processor delays. So for example, this really gets into some more technical things I don't want to talk about for a long while. But at some point, we're going to be doing this magical thing called pipeline to make our computer run ludicrously fast. The problem is, when we pipeline, sometimes I might say, okay, I want to do A plus B and save it to the output register, then immediately want to do something with that result. When you're pipelining, if I tried immediately accessing with the result, that result wouldn't be available as soon as that command is finished, because it would start executing other commands. And so if I try accessing it immediately, that would give me some completely different data. So the rest of my execution absolutely depended on the data from that addition operation. The call function might call something like processor delay, which would just wait for all that data to reach that final output register, and then everything would be back to normal. And yeah, and same thing if you're doing a really, really big memory system. If I'm doing saving to some ridiculously huge memory system, it might take several cycles for that data to actually get saved, so I might use a call function to delay there. And it's not just used for processor delay, but really just anything that alters the processor, the way data is processed physically. Delay is a really obvious example, that's why I'm using it. But yeah, anything that physically alters the way the processor is working and the way it's processing data, like maybe holding it like I'm doing. Or maybe you have an operating system you want to interrupt or something. Maybe maybe your operating system has some command to print a bunch of data to a screen. I don't know. That would also be done with the call function. So yeah, that's what the call function is used for. And that brings me to these magical 4 registers. What do they mean? Not much, actually. These are just data that you can save for certain functions. Let's say one of my functions is multiply. And I want to multiply 3 numbers because this is a special multiply command. So I might store the 3 numbers I want to multiply in call 1, call 2, and call 3. And in call 4, I might store the address that I want to return to after this multiplication function is done. It's just a place where I know the data that this function is going to use is going to be. That's pretty much the purpose. I cannot say that word of these 4 registers. They, again, most part, they're general purpose registers. So yeah, that's the entire SRCIS 2.0 instruction set. That's it. That's everything there is to it. So, yeah. And so hopefully you understand the instruction set now. It's not the hardest instruction set in the world. It's pretty simple overall, but it's going to run pretty fast. Because if you notice, all these functions on here, they might be simple, but they're all really fast. The slowest thing on there is what? Addition? And I mean, how fast is addition? You can get addition in 2 ticks. So 2 ticks per function, plus saving and loading. Yeah, this thing's going to run stupidly fast when we're done with it. That's the power of RISC instruction sets. But hey, yeah. So anyways, hope you enjoyed. I hope you learned. And I guess I'll see you next time, where we'll actually start talking about how to lay out a processor which implements this instruction set. And again, if you don't like this instruction set, you don't have to use it. If you want to download x86 specification from the internet and use that, first off, good luck. Second off, seriously, good luck. You were going to need it. And third off, you can do that. Nothing's stopping you. But yeah, hope you enjoyed, hope you learned, and I'll see you next time. Hello everyone, it's Benny, and I'd just like to apologize for being so, well, hyperactive in the recording, because I don't know what got into me. I recorded too late, and it definitely showed in the recording. But yeah, I still hope you managed to learn from that, and yeah, so I'll try to do better next time, I suppose. So thank you. Hope you enjoyed. Hope you enjoyed this. And I'll see you next time.